I think it's time to start then for us, and welcome everyone to CPPC webinar on Friday. Now, it's my great pleasure to introduce our today's speaker, Tjonnie Lee. I will quickly run through his quite impressive bio. Tjonnie did his undergrad at Cambridge, the master's at Cambridge, and then he moved to Netherlands and did a PhD there at that National Institute of Subatomic Physics in 2013. And then he spent his postdoc at Caltech doing gravitational waves. And in 2015 already, he got a faculty position in Chinese University of Hong Kong, where he is a professor of physics there. Now, Tjonnie is well-known, young but very well-known expert in gravitational wave physics, and he's also interested in the applications or implications of the gravitational waves to cosmology and astrophysics, and he will be talking about today about gravitational waves and how to explore the dark universe through the gravitational waves. So over to you, Tjonnie.
Thank you so much. I must say that that's way too much praise, but I'll try my best to convey some of the recent results that the LIGO-Virgo collaboration have come up with. But also at the end, I'll talk a little bit about, and just with the focus on ground-based detectors, on how to constrain, you know, for example, dark matter in the form of ultralight bosons. So if at any point things aren't clear, feel free to raise your hand or just speak up and just ask questions, right? I think this is a fairly relaxed setting. So as the title saying, I'll talk first about the status and the prospects. So I'll give a quick review of things, and then I'll end with a special topic that I've been working on recently as well. Now, I know that not everyone here may have followed this very tightly, so I'll go give a very brief introduction first. This is something that I think most people will have somehow seen or heard about. This is the abstract for the first detection. And I just highlighted a few keywords that I'll be focusing on. So in particular, all the detections that we've done so far are collisions of compact objects, either black holes or neutron stars, and we'll be looking at kind of how they merge and kind of what information can we get from these events. So I'll just show one of the stock animations, simulations for binaries. So here you see the two black holes. This is the first event, and what you see is the system starts where the two objects just orbit a common center of mass, and then as they radiate energy and angular momentum, the objects come closer, causing the objects to spin up, right? The orbital frequency to spin up, and therefore they emit more gravitational waves, so the amplitude and the frequency go up, and you see this runaway process where the objects get closer and closer. The amplitude gets bigger and bigger and bigger, up to a point where the two objects, and we'll see that in a second, they touch, they merge, and they form a single black hole, and then it radiates away any excess energy and angular momentum in the so-called ring down phase. So that's basically what I'll be focusing on. And I'll just close this one out. So if we actually take a more careful look, then we can more or less separate the signal of a compact binary into three parts. The first part here at this side here is the so-called in-spiral, where we have quasi-circular orbits, and the frequency is fairly stable, and as it evolves, there's only a slow drift in the frequency and in the amplitude. And as the two objects get closer and closer, we go into the merger stage. This is where the non-linearities really pick up, and the process is fairly quickly ramping up for the two objects to touch and to merge. And then finally, once they've merged, there's a period of time, so-called ring down, where the object then reaches a quiescent state. And so on both sides, we can use on the in-spiral side, we can use post-Newtonian theories or effective one-body theories. And then on the ring down side, there are perturbation theories that help us understand this process from a theoretical perspective. And then somewhere in the middle and also towards the end in the ring down, we also have access to numerical simulations, numerical relativity, to get a more complete picture understanding of this process. So that's the morphology of a binary, and there are generally two ways in which we search for these in our data. And so here we have the so-called unmodeled searches, where we look at coincidence, excess power in the time frequency plane, typically. And this pretty much requires minimal assumption on the signal morphology. So here we only look at, when we have two detectors, we can correlate their power. And so we don't have to explicitly assume the waveform that we're looking for. On the other hand, we have a modeled search, where we use a predicted waveform by general relativity. These typically consist of the in-spiral part, where we use post-Newtonian theory, effective one-body theories, and then we supplement it with numerical understanding. But the upside to all of this is that we can construct so-called optimal filters. Right? If we know what we're looking for, we can devise optimal strategies to find them, even if the noise amplitude is generally much bigger than the signal amplitude. And once we have filtered all of this, we typically rank the candidates. So we also have to have a step where we evaluate how likely these are actual gravitational waves from astrophysical origins, or whether they are from terrestrial origins. Could be glitches in the detector, could be a bus coming by, could be an alligator, could be anything. So in terms of an unmodeled search here, I'm just showing, again, this is for the first detection. So you see on the left, you see Hanford, and on the right, you see Livingston. These are the two LIGO detectors. And so what we can do is we can look at the two spectrograms, and we can compare them, especially the power distribution in the two detectors. And there, from there, see if we can find some cross power that we can then accumulate to look for confidence in a gravitational wave detection. And so, as an example, this was for the first event. This is the so-called detection statistic. So this is just a measure of the loudness, and the louder it is, the fewer. Here in the solid lines, we can see the so-called background. This is what the noise artifacts typically give you, and you can see a nice straight line here. So there's a number of events, a number of triggers, and then we see here, these are the two background. One is whether you leave the signal in or whether you don't leave the signal in. And then here you see the detection with a particular detection statistic, and of course the number of events is 1. And that's how, for a generic transient search, we determine what's the likelihood. And for the first detection, this was determined to be bigger than 4.6 sigma, but not reaching exactly 5. Now, similarly, for a modeled search, we do match filtering. And so this is just a very simple, basic demonstration of what this is. So in blue, we see let's say the full data set, and then in red, we have the template. We have the thing that we're looking for. And as we slide this red over the blue, we can see that at some point at a certain time, we see that the so-called cross correlation has a peak. And so we look for these peaks in order to decide, what are the candidate events that we want to consider. So again, I'm just playing this again. We slide the red over the blue, and as soon as there is a match, we can see here there's a peak, and then it dies down again. And so by looking at these peaks, we determine our so-called triggers, our detection candidates. Now, For the modeled search, we search through them in a so-called parameter space, right? And so we need templates throughout this parameter space. So what we do is we construct a so-called template bank. And so these are waveforms that we have and that we filter over. And all of these points represent a particular configuration, because this is mass 1, mass 2. And then we use these waveforms. And so we filter the data with tens of thousands of templates in order to obtain all the detection candidates. And this is the example of the background that we have, and then this is the detection here. So again, the detection statistic, the black is the background. If you leave this event, if you assume this event to be part of the noise, and here is the background if you exclude this to be part of the noise. And you can see here, here in the top bar, we for the first event, we reached over the 5.1 sigma. So that's more or less how we find gravitational waves just from the raw data. Now, once we have found them, we infer the properties. Again, this is the example of 150914. This is the first event, and we do Bayesian inference. So this is Bayes' theorem, where our starting point is the prior, and then the likelihood, which depends on the data. The prior is a prior information about the system parameters, and then we use Markov chain Monte Carlo methods to sample the so-called posterior. And so the results are figures like these. So this is mass 1, mass 2. This is again the first event, and you can see a probability distribution for the mass. And here in this case, it's about 36, 37, and here is there's like 29. Right? And so if you remember the numbers for the first detection, then this is roughly what we see. And here on the right, we do the same thing, but for spin. So this is so-called disk plot. This is a spin magnitude, and then there's the direction of the spin. And so you've got the primary and the secondary spin that we measure again in the same process. So typically, if we look at these Bayesian inference, our parameters are the mass, the spin, the distance, the orbital inclination, the position in the sky, and everything. So the full parameter set that we consider. So that's what we do these Bayesian sampling over. So we get the posterior in that same number of dimensions. Okay, so I'll give a very brief, and this is supposed to be very brief, overview of what we've learned. And this is called so-called GWTC1. This is the Gravitational Wave Transient Catalog. And so the first version was for the observation runs 1 and 2 for LIGO and Virgo. And here we can see the different masses. Here on the horizontal lines are the masses. And then in the blue, you can see the ones that were detected using gravitational waves. And then in purple are the ones that we know from electromagnetic measurements. Dark orange is the one binary neutron star that we found, and then all the other neutron star masses that we know are there for comparison. So this is going to be a very, very a brief fly through of the events of 0102 and what we've learned. So I'm going reverse chronological order. So for GW 170817, this was the binary neutron star detection. And of course, the highlights were that this is an actual binary neutron star, so we can see it from the masses that they must be in a neutron star range. But more notably, we saw an associated gamma ray burst and a kilonova from this. So this is the LIGO sky map and a LIGO Virgo sky map, and you see the Fermi sky map, and then inside you can see the optical telescopes that have taken pictures of this event. Now, by measuring the binary neutron star and the gravitational waves from them, we were able to put some sort of constraints on the nuclear equation of state. So these are the tidal deformability parameters, lambda 1, lambda 2, for the two detections. We have been able to measure the Hubble constant by assuming that we've observed the event in optical telescope, so we can find out what the galaxy is, we can get the redshift, and then we get the luminosity distance from the gravitational wave detection, and we can combine that into a Hubble constant measurement. We've been able to compare the arrival time of light versus the arrival time of the gravitational waves, which gave us a first real constraint. No, I wouldn't say real constraint. First, stringent constraint on the speed of light versus speed of gravity. So how fast does a gravitational wave travel versus how fast does it compare to light? And again, here we see a fairly stringent result compared to the speed of light. So that was the BNS detection. We saw also 170814. That was the first detection that was made in all three detectors. So instead of just Hanford, Livingston, we also have Virgo in Italy. But it also gave us the first Hubble constant measurement without an electromagnetic counterpart, where instead what we do is we statistically assign likelihoods to known galaxies, and using that to obtain all the possible redshifts at which this event could have occurred, and then we can extract a Hubble constant measurement from that as well. Okay, so we have 170608. This was more or less the first black hole in the electromagnetic range. So this is what we've seen, and I'll go back to this slide over here. So this is really within the range of the EM black holes that we know, and so that is this event over here. And then there's a bunch of events that are that were reported, but from kind of physics understanding not too interesting. And then going back to 150914, of course, that was the detection of gravitational waves outright, but also kind of our first time that we use gravitational waves to test the dynamical nature of space-time. This is the post-Newtonian order and the constraints that we've been able to put on these post-Newtonian orders. So in blue, you can see the pulsar results, and then in orange, you see the bounds that are put on various post-Newtonian orders through gravitational wave detection, direct gravitational wave detection. Okay, so so that's really kind of in a nutshell. That is how kind of the stuff that we've learned from GWTC1. And so what I want to move on to next is to talk about GWTC2, and that is the second catalog, or the second iteration of the catalog. And this was this combines also the first half of the third observation run. Okay, so 03 is a third observation run, and so the first half is now combined into so-called GWTC2. So we can see the same graveyard video here, and oops, sorry, we see the same graveyard video here, but now we see a much bigger population of sources, right? It almost starts to get too difficult to put all of these events into a single figure. So I think that, well, I hope that by the next time we release another catalog, we will stop doing this, because I think it's starting to get harder and harder to visualize. So what I'm showing here is a simulation, but all the different events kind of run simultaneously next to each other. It's just a little bit of amusement. So you can see all these binaries with different masses, different mass ratios, different things, and you can see them colliding and forming a single black hole. So again, but now slow down. You can see, and you can look for your favorite gravitational wave event, out here. Okay, so what have we found in GWTC2? So the first and arguably the most obvious thing is, of course, just the number of detections. And so what I'm showing here is the so-called effective binary neutron star VT. VT is the volume. So this is the, if I take the sensitive distance of the detector. I cube it to get the volume, and then also multiply by the time. So this is how much time am I observing given a particular volume, and I can offset that with the cumulative number of detections. And so you can see for O1, O2, and you can really see the steady progress all the way up to O3A, which is the first half of the O3 run. So that's all those events that were included into this GWTC2, right? And you can see it really follows very nicely the expected trend that we see. So this also reflects the improvement in the detector sensitivity, right? And that's why we really see, so the VT is really going up, and then the cumulative number of detections as expected then goes up with this. So if you look at here, this number is the total number of detections that we have. So I've stopped counting them. It's a little bit over 40 total now. Okay, and this is a highlight of all the mass parameters. So on the x-axis we see the total mass, and Q is the mass ratio. So this would be the smaller mass on the numerator, and the larger mass on the denominator. And you can see this plane of all the different, in gray and in colors, all the different events that we've seen. The ones in colors are the ones that we give special attention to. These are published separately, whereas the rest, the ones in gray, are typically being summarized in the catalog paper, and then we use them to construct rates statements. Okay, so the first event that I want to highlight is GW190425, and this is really, if you look at the masses, these are really really low masses, right? So this is mass 1, this is mass 2, and you can see two different colors here. The one in blue is when we put no or very little spin restriction. Whereas if we put more spin restriction, if we believe them to be neutron stars, then we put a tighter spin condition on them, because we know otherwise the neutron star would break up if they spin too fast, and that gives us a much tighter constraint on the masses. But nevertheless, right, the evidence is very clear. This is a very low mass detection. Now, if we compare this to the known galactic binary neutron stars, again in orange we see the constraint, but this is now the total mass using a restricted spin, or in blue if we do not restrict the spin, and then we can compare that to the dashed line, which are the known galactic binary neutron stars. So even though we've seen this event and we know that it's a very low mass, we also see that this is very far away from all the binary neutron stars that we've seen in the galaxy. In fact, if you take this, then this result is more than 5 sigma away from the distribution of galactic binary neutron stars. So despite this limited kind of information, we still learn a lot, right? As I said before, so the total, but also the chirp mass is 5 standard deviations away from the galactic population mean, and so this kind of allows us to think about how would events like this have formed if we believe them to be neutron stars. So for example, did they form in an isolated binary evolution? So the two stars evolving, one going supernova first, and then the other one going supernova. But in that case, we would need kind of ultra tight orbits with almost like a sub-hour orbital period in order to be able to create such a heavy system, because otherwise the one supernova will blow the other one away. So the models are such that It is possible to still have them formed as an isolated binary evolution, but it would put restrictions on the types of orbits that they could have formed in. We could also have a formation scenario where we have a massive neutron star being replaced with another neutron star through dynamical encounter. So, so we have, you know, a star that was orbiting some other massive neutron star, and then through some dynamical process, a neutron star gets slotted into this binary. Now, another idea that has been floated is the fact that we see such high masses is because of gravitational lensing, in particular strong gravitational lensing, in such a way that, you know, that these are not the actual masses that the source masses. That instead these are the observed masses, and if you have gravitational lensing, then there's a redshift factor, and so it could appear to be closer to you because it's been magnified, making you think that, you know, it is actually, you know, it's actually heavier. Now, we know that, you know, given what we know about the optical depths, so this is given what we know about the lensing probability as a function of distance, we know that this is rather unlikely given this system. But nevertheless, it could be a way to explain why this event is so much more massive than the ones we know. Of course, there's also the possibility that these are black holes instead of neutron stars. Now, that would mean that, you know, we've seen black holes falling into so-called mass gap. This is the gap that we believe that between neutron stars and black holes, that there's a region where we don't expect compact objects if we look at simulations. Of course, there are many counter evidences that, you know, the mass gap does not exist or is very limited in scope. So this is one possible explanation. These could be binary neutron star merger remnants. So when you have two binary neutron stars merging and then, you know, forming either a very heavy compact object or, you know, somewhat light black hole, in which case we would circumvent the so-called mass gap. And finally, another possibility that these are black holes, but not of stellar origin, but of primordial black holes. Right? So these are black holes that are formed in the early universe instead of through stellar collapse. And so also these have much fewer restrictions on the mass that they are able to acquire. Okay, so if I switch 1904 12, this is an event that had an extraordinary large or small, depending on which way you look at it, but it had a very high mass ratio. Okay, you can see here different colors because they represent different different waveform models. These are different you know, models that we use to do the Markov chain Monte Carlo, the Bayesian inference. But all three of them agree that the mass ratio is, you know, is somewhere around, if not higher than 1 in 3. And this is actually the first time that we've seen an event that has such high mass ratio. So this is a mass 1 and mass 2. Again, this is like, you know, 20 something here. And oh, sorry, this is the wrong figure. Not the wrong figure. This is another event. This is 1908-14, which is the second event that had very high mass ratio. So now we see here 23 and 2 point something. So this is almost getting close to 1 in 10. So these two events represent two events within the second catalog that have very high mass ratio. Now, why is high mass ratio of such particular interest? Well, the reason is because when you have high mass ratio, then we expect to see more contribution from subdominant gravitational wave modes. So the way to think about this is when we have gravitational waves, the leading order, you know, spherical harmonic mode is the 2-2 mode, where 2-2 stands for the you know, L and the M's. But if we have very high mass ratio, then we expect these subdominant ones to be measurable, even comparable in terms of strength, and this would then be the first time that we are able to observe these subdominant modes. And so these two events give us that opportunity. Now, when we have higher order multiples, we are actually able to much better constrain the gravitational wave parameters. And the way to think about this is because, depending on the orientation, so if we see the binary face on, right? So if the plane of the orbit is, if the normal of the plane to the orbit is pointing towards us, we can see the full binary in circular motion. When it's face off, we would expect to see only, only on the side, we can only see the line. And, when we have different modes, we can actually, we can discern in which direction the orientation is pointing towards us. And so, for example, here indeed, this data is the orbital, inclination that we are able to observe. And here d is then the distance. So if we only use the dominant multiple, then we don't have enough information to discern whether the orbital inclination and the distance. But when we have multiple modes, we can actually analyze them almost separately in order to get information about the orientation of the binary with respect to us. And this is just a highlight using 1904-12 of how, when we use higher order modes, that we get much better constraints on the inclination and then also on the distance. Now, what is the evidence that we have for these higher modes? And so what I'm showing here is the following. So here on the x-axis is rho, is the signal to noise ratio. And in orange, we see the signal to noise ratio that we infer by only considering the 3-3 mode. Okay, so this is the contribution to the entire signal, assuming only the 3-3 mode. And we can see that the signal to noise ratio is 3.5, let's say. Whereas if you see in a dashed line, this is what we expect just from a pure noise contribution. So if this distribution, if the orange distribution lied somewhere here in the SNR1, then we would say that there's almost no strong evidence for this precession. Sorry, for the 3-3 mode. Whereas in blue, this is actually our evidence for precession. And so you can see that the evidence for spin precession is far weaker than the higher modes that we have. Now this also plays out here in the bottom, where we look at the so-called base factor. So this is the betting odds. This is the how much more likely is one hypothesis versus another hypothesis of having higher modes versus just a dominant multiple. And again, this is precessing versus aligned. So when the spins are aligned, and you can see that indeed this number is always bigger than 1, whereas 1 means they're equally likely. So here we've got 4 times more likely that they're higher modes versus just the dominant mode. And again, the labels here, Bilby, Lal inference, Rift, are just the different incantations of the Markov chain Monte Carlo that we've done. And even using different waveform models, so effective one body or phenomenological or kind of a numerical relativity inspired, you can still see that these numbers are generally above 1. And so this is evidence that we've seen higher order multiples. Okay, similarly here, this is for 1908-14. Again, I showed this event, so this is 1904-12 and 1908-14. Both are very high mass ratios. And here again, we can see rho. So again, this is the signal to noise ratio, and the signal to noise ratio of the 3-3 mode is very significant compared to compared to if there's any spin precession. So in both cases here and here, we see little evidence, for spin precession, but we do see evidence for 3-3 mode. Okay, so in terms of conclusions, the we've seen twice 2 black holes with significant asymmetric component masses. And so we've been able to identify that at least the second most important multiple, which is the 3-3 mode, makes a significant measurable contribution to the observed data. The orientation of the binary, therefore, is much more accurately determined, and it really opens up the field for more precision measurements. So we're able to place, for example, tighter bounds on the mass ratio and the spin. Whereas 04, there should be 12, not 25. 04, 12, I'm getting also always mixed up with the numbers. Shows marginal statistical hints for precession. 0814 shows very little statistical hints for precession, but the secondary mass for the 0814 is actually too large to be a neutron star. Right, so I can go back to this slide here, right? If I look at, this is 2.5, 2.6, 2.7 in that range, and considering what we now know are the most likely models for the nuclear equation of state, the maximum mass actually does not reach this number. So this actually imposes a conundrum in terms of what we know or what we think about this system. So, speculations galore. These could be exotic compact objects, could be, light black holes, again, primordial black holes, all sorts of things. Everything is more or less kind of out in the open. Okay, now coming to maybe the, I would say for me, also the most important event. This is 1905-21. Important because this is actually among the first times that we've seen a black hole in the so-called pair instability mass gap, but also where the remnant of a black hole is more or less conclusively an intermediate mass black hole. So you can see here the mass 1, mass 2, and you can see that the component masses are really on the high side. But then if you add these two up, the total mass then ends up falling into intermediate mass black hole range. So indeed, if I look at all the past detections before 1905-21, and this is the mass here on the y-axis, and here on the right we can see some simulations of stellar evolution, and you can see this mass over here. These are the two component masses, and this is the resultant of the remnant mass, and you can really see that it falls nicely in this in the so-called mass gap. So that's it's a relatively special event in that sense. Now, because the signal is very short, right? The signal is very heavy, which makes the time until it collides very short. Now, because of the shortness of this event, it actually opens up a lot of speculation about alternative explanations for this event. And so one of them that we've considered is a so-called cosmic string. These are topological defects that could create a burst if they snap, or if they undergo some dynamical situation, and they can give you a gravitational wave burst in this case. And so this is the best matching cosmic string template. But again, we can more or less see that the data does not really favor this explanation. We've also looked at other explanations. They include head-on collision, highly eccentric orbits, and so on. Excuse me. And that's because this short event actually allows us to fit many things. So indeed, this was a high mass binary black hole system. One of the components in the pair instability mass gap, the final merged black hole in the IMBH range, intermediate mass black hole range. We've considered a bunch of other sources other than quasi-circular. sources, eccentric orbits, cosmic strings, supernovae, head-on collisions. And also another, I think a very interesting possibility is now that we know events of this class exist, these events are actually potentially observable both in LISA and in ground-based detectors. So a topic that has been recently quite receiving a lot of attention is to use both space-based detectors and ground-based detectors to observe the same signal. So you start with a very low, very low frequencies or very large separation orbits, and you can see them in let's say LISA, but also other planned space-based missions. And then, as time progresses, the system goes closer and closer. At some point, the frequency ramps up and it would go into the LIGO band. And this is actually an example of one of the events that you can observe in both detectors. So this would kind of be the, a different type of, kind of a multi-band observation. This is a particular example. The remaining, let's see how much time I've got. I've got 10 minutes maybe. So I want to talk a little bit about some recent work that I've been doing. And that is on whether we can use these detections that I've shown just now to look for dark matter imprints. Now, this is a kind of an overview of the various dark matter effects. And I'm obviously not going to consider all of them. I just want to show you kind of that there really is a big landscape. You can have dephasing of the extreme ratio in spirals. We can actually have we can have some axion interfering more or less with the detector itself. So we could even take a look at the setup of the detector to see if we can find any dark matter. The influence of just primordial black holes and so on. The thing that I want to show here actually has to do with the spin measurement. So the context that I want to bring up here is the so-called ultralight bosons. And their influence on the spin measurement. So we know that the spin measurement with ground-based detectors such as LIGO and LISA are usually inconclusive. Okay, so these are just 3 examples of the spin disks that I mentioned before, and generally I don't know how to, I don't really have a good sense of what their spins are. But it is important, right? The spin actually reveals a lot of information, and so one of the ways in which we can learn something about dark matter is the coupling of the black hole spin to, in this case, the ultralight boson and the super radiant instability. So one thing you can consider is that if you have the hypothesis of an ultralight boson, then when the process of super radiance sets in, then you create this cloud of bosons where the energy is actually extracted from the black hole. Okay, so there's this semi-classical wave amplification process that then extracts energy from the black hole. And what you end up having is that the black hole spin actually goes down in order to extract the energy to form this ultralight boson cloud. Now, of course, this cloud will then radiate away into, could be in light, could also be in gravitational waves, and then you get a stable black hole with a spin that actually is has memory of the super radiant process, and so the spin actually ends up following the physics of the super radiant process. And of course you can have a second mode that then sets in and then to further spin down the spin. So another way to look at it is here in the mass spin plane. So imagine I've got an initial black hole and then there's the super radiance process that sets in, which then spins down the black hole onto a particular line here. And this is so-called Regge trajectory. And so if the if the ultralight boson and the super radiance process actually exist, what we expect is for black holes in this region to actually excite, if the conditions are right, excite the superradiant process, and then the masses of the black holes to preferentially lie on or below the so-called Reggie trajectory. And so that's something that we could probe, right? Because, you know, we do in principle have access to the spin measurement even within LIGO and Virgo. And so this is just an example. This is using all the known kind of black holes that we have. And here you can see all sorts of, you know, the Reggie trajectories given the different masses of these ultralight bosons. So this is 10 to the minus 11 electron volts all the way to the minus 17. And you can see that depending on the mass of the ultralight boson, it traces out different Reggie trajectories, and therefore you have different so-called exclusion zones. I wouldn't really say exclusion zone, but these are regions where we expect fewer of the black holes to black holes masses and spins to be. And so we can actually use this process, right? So if there is a critical spin, then all the spins are then expected to bunch around the critical spin for the superradiant instability, as opposed to just the spin being able to take any value that it wants. And so that's actually what we've done. We've set up two hypotheses. So we set out to analyze the whole population of binary black hole detections, and then to look at their spin. And so we actually model the Reggie trajectory given the various timescales for growth, and then for the superradiance rate, in order to calculate these critical spins, right? So these trajectories, and then say, okay, well, what we expect the critical spin to be given a particular mass. And so we actually go through that, and we set up two hypotheses, right? We use the data to run two hypotheses. And one is the so-called boson model. So the boson exists, and can then, using superradiance, spin down the black holes, so that the values of the spins tend to be following the so-called critical spin. Okay. And so depending on which critical spin lines that it follows, or if the timescales are not long enough for this to happen, then it's just a spinnet formation. So this is the so-called boson model. And of course, we have the so-called astrophysical model, where we assume that there is no boson there, and there the spin at merger is just the spin at formation. Okay, so these are the two models that we can then use the population of black holes that we've detected. We can actually compare and see, okay, well, what do we expect? Well, do we see any statistical evidence that there's these preferential values along the critical spin lines? And so what we do is so-called hierarchical Bayesian inference. So it's just a framework to bunch together many different measurements to then infer meta parameters or hyperparameters, which then classify the whole population as opposed to individual events. This is detail that I don't I'd be happy to discuss, but I don't think it's very relevant at the moment. And so what we did is we actually looked at a boson scalar field with a particular mass. So let's say 10 to the minus 13, 10 to the minus 12, and then also no boson. There's no boson. And so we generate binary black holes with M1, M2 uniform in this mass range from 5 to 50, and then everything else uniform in luminosity, distance, orientation, and everything. And this is just so that we can check whether this is actually observable, right? Whether an effect like this would be observable. And so we consider two different kind of spin formation. And this is purely a mock data challenge, but the result is as follows. So if we look at the number of high signal to noise ratio detections, what we can do is we can quantify how many detections do we need in order to observe this effect. So this would be the astrophysical model, and we can see that it quickly gets disfavored because the underlying model here is a particular ultralight boson model. And so the point here, which is about 100, this is how many events that we need in order to conclusively say that the astrophysical model is incorrect. Okay, so that the spins do not follow necessarily the astrophysical model. As on the other hand, if we want to take a look at when can we confirm the the actual existence of this ultralight boson, we would need around the same number of events, given given the parameters that we give it, given the mass of the ultralight boson. So it is something that in principle is possible. But it would take, hundreds, if not more, events that we can see this. Of course, the expectation, if we go, for example, into LISA and future generation detectors, that this will actually be immediately possible. And again, this is just a mock data challenge where we look at, can we also actually infer the spin distributions? And so if we put in the right one, we can see that we actually retrieve the correct one, so the blue one. Whereas if I use a boson model on an astrophysical one, I get the blue one, which follows a weird distribution. Whereas if I use a boson model on the boson events themselves, I get that the spin at formation is nice and uniform, which is exactly what we expected. Now this is just a mock data challenge, right? Here we simulated, we did everything, we did everything ourselves, and so we should get what we get. And this was really just to compute how many sources do we need in order to detect these. What we actually do, or what we have done, is we've looked at 0102, and we applied to, so this would be GWTC1, and we applied it to all the 10 events. We more or less retrieve the prior back, so we don't see any evidence for this boson hypothesis within this mass range. The Bayes factor, which is again the betting odds, is 1 to 2. Again, it's not conclusive. Now that's using the first 10 detections, so GWTC1. Actually, today on arXiv appeared a preprint of us that we wrote, where we actually report on the GWTC2. So I hadn't had time to, I just received notice that this was posted. So what I can show you is the actual paper. And actually there is some interesting result here that I know. And so let me see if I can make this bigger. So here, what we have is a posterior for the mass of the boson, excuse me, given the data. Okay, so this is the mass of the boson itself, and this is the posterior. And you can actually see, if I use the second catalog, right? So these are the 40-something events that we have, and that's in blue. We actually see that there's a region of the parameter space that the gravitational wave events that we've seen so far are already excluding. Okay, so the 40 events that we have now already started to exclude a particular region. So it's about 10 to the minus 13, 10 to the minus 12 and a half. That mass range is now, at least according to the ultralight boson model, is now being excluded. Now the orange ones are where we take away 2 events. That would be 190412 and 190517. Those are the rapidly spinning ones. So this is just for us to confirm that indeed the rapidly spinning ones are actually causing the exclusion of this particular mass range. And we can understand this if I go back to this picture over here, because given a certain mass, or actually this one, given a certain mass, if I see a highly spinning black hole with a particular mass and a particular spin, then I would be able to exclude the existence of an ultralight boson in that particular mass of the ultralight boson. So that's basically what these two figures, what these two graphs show you. So that's more or less all that I want to say. I think I'm a little bit over time, but I have some extra time for any questions or comments that you may have. Thank you very much for your attention.
Yeah, thank you very much, Tjonnie, for very informative and very good talk, very interesting. So we have time for questions. So, who wants to go first?
So I can ask a question about the Hubble parameter constraints. You mentioned that you can even get a constraint if you don't have an electromagnetic counterpart observation by essentially marginalizing over the redshifts of candidate host galaxies. So by doing that, how much sensitivity do you lose? And would that be offset by the fact that you observe these events more frequently than ones with electromagnetic counterparts? Can't hear you.
Can you hear me?
Yep.
Okay, sorry. Yeah, I muted myself. Okay, I can show you the figure. So this is the constraints that we have with the electromagnetic counterpart. And if I assume that I don't have one, then the degradation is quite stark, right? You can see here that the degradation is getting very stark if you look at the numbers here. So this would be 20 to 140, where there's almost no peak, versus a fairly pronounced peak. So I would say several times more stringent bounds. Yes, you're right. So because this happens much more often, I can accumulate statistics, right? I can add many sources. Now the only thing I can say is that there have been studies that the landscape will still be dominated by the ones with electromagnetic counterparts. So those will you would need hundreds, if not thousands, of events before like a statistical method like this would kind of alone would supersede the ones with electromagnetic counterparts. Now, of course, we don't know the rate at which these counterparts show up. So it could be 1 in 1,000, in which case the methods could be comparable. Combination of the two would, of course, be best, but expect at least to need hundreds, if not thousands, of events before this could actually be competitive with having an electromagnetic counterpart.
Thanks.
Did you repeat that exercise with the run 3 with the latest?
You mean this exercise with?
Yeah, this one here, right? That was for the run 1 and 2.
It is being prepared. I have not kept up with the latest, so I don't know what the results will be. I expect that the problem also is because is catalog completion, the completeness of a catalog. So if the event is too far out, then our galaxy catalog may not be complete. And so we also run into the trouble of, how confident are we to using these events and correlating them statistically with known galaxies if we know that at that distance the galaxy catalog is incomplete. So that really is an interesting statistical game that we have a whole subgroup working on. I don't know how the latest results are going to look. But there is a paper on it which I can actually this is if you want to keep up to date with the latest and greatest of the LIGO papers, they're actually in papers.ligo.org. This is often where I even get my information from, so there are too many other telecons going on. But there was recently a paper posted on these Hubble constant measurements. So this is using GWTC1, which is August last year, which looks at different Hubble constants using the whole catalog. I know that they're preparing the same thing for GWTC2, but I wouldn't know the exact time scale of this.
Yeah, thanks.
But it is being prepared. It is being prepared.
Yeah. Other questions?
May I ask a question?
Of course.
Yeah.
Okay, so I have a question about the you exclude some mass range for the light particle that plot. Yeah. So what's the bump about this dash 9? Is that, does that mean some evidence for something, or yeah?
I wouldn't call it really evidence. If you look at kind of, this is where you more or less expect the baseline to be. We expect some natural fluctuation, also with where there are more detections or not detections. I wouldn't classify this as a detection. So thank God this is recorded. So I always have proof that no one claims that I've said this. No, I think this is statistical fluctuation. Especially if you take away the two highly spinning ones, you can kind of see this kind of this bumpiness, which I think, given the precision with which we can measure things, I expect this to just be statistical.
Thank you. So I have another naive question. So does this super radiance effect assume this light field is dark matter, or just?
No, this is just generically a kind of an ultralight boson that could undergo this super radiant instability, but there's no other assumptions made on that it must fully explain all the dark matter that we have. No.
So that basically say that if there is some light fields in nature, then it can be excluded just by gravitational interaction. So.
Yes. Now there have been kind of studies done on that in that area as well. So there are other kind of exclusion or other constraints from other experiments as well. The point here is that this super radiant instability would typically happen only around black holes, and it wouldn't really magnify the effects of these ultralight bosons. And so we expect these effects to be very pronounced close to black holes, and that's why we look for them with these detections. Whereas on a longer scale, the effects may be more subtle, so the constraints may be weaker that way.
Okay, thank you very much.
Any other questions? Maybe in the interest of time, so because let's thank Tjonnie again, but I think she has a little bit more time to answer more questions if there are more questions. But if anyone has to leave, he should feel free to leave if that's good. So thanks a lot, Tjonnie.
Yeah, thank you, everyone. Yeah, I have more time, so I'll hang around if the host doesn't cut the